our speaker, isn't he?
Is this on?
No, on the top of the switch to unmute.
Okay. Is that working?
Yeah.
Great. Okay, so I've entitled this talk The Hermit in the Machine, and in a few slides that might actually make sense. But let me first start by giving some motivation about the area we're working in and what we're interested in. So, as you all know, when you're writing your programs, there's often a trade-off between the clarity of the program and the efficiency of the program. Not always, but this is a common problem. And one thing people like to do about this is perform some sequence of transformation steps to transform a clear but inefficient program into a less clear but efficient program so they can actually run it more usefully. And you can either think of this in the context of you've got a program and you want to optimize it, or you might think of it in terms of having a specification and you want to generate an implementation from that. And what we're interested in is mechanizing this sort of transformation in the context of Haskell programs. And I emphasize mechanize here because we think that mechanizing it is better than doing it with pen and paper because it's less time consuming if you've got a good mechanical assistant, and it's far less error prone. It's very easy to make errors when you're just working with pen and paper. And it also leaves you with the original source file that you can just generate your efficient implementation from, which you can use as a reference. So there's been a fair amount of work in this area before. There's been various transformation systems developed, HERMIT, Path and Ultra, a few that I'm aware of. If you're aware of others, please let me know. But the thing about all these systems is they all operate on Haskell source code or some variant thereof. Now, I started that sentence with but, and you might think, what do I mean but? Isn't that exactly what I just said I want to do? Well, it sort of is, and it sort of isn't. Okay? So what is Haskell source code? Am I talking about Haskell 98? Am I talking about Haskell 2010? Do I want some GHC extensions? If so, which extensions do I want? Okay, so there's many different versions of Haskell, so you've got to decide which one you're working with. And new GHC extensions are coming out all the time, which as a program it's great, but as someone who's writing a tool to transform Haskell programs, it's quite hard to keep up with them all. So we've taken an alternative approach, and we're interested in transforming GHC's intermediate language, GHC core, which I guess some of you are familiar with and some of you aren't. Okay, so this is the language that gets produced after GHC is scanned and parsed and type checked. It builds this internal representation. So I'll show you that to start with, for those of you who haven't seen it before. I'm not expecting you to memorize that, but just to give you a flavour for what it looks like. So this is much smaller than Haskell source syntax, okay, which makes it a lot easier to work with when you're applying transformation to this language. It's a lot easier because we've got a lot less cases to consider. It's a lot easier for us to implement as well because we have less cases to deal with. It's also more stable than Haskell source syntax. As I say, GHC language extensions come out all the time, but the GHC core language changes far less frequently. Okay. So the machine I mentioned in the title is GHC. So I should tell you what the HERMIT is next. So HERMIT is an acronym, stands for Haskell Equation Reasoning Model to Implementation Tunnel. I'm never going to say that again, it's always HERMIT because that's too much of a mouthful. And as a one-sentence summary, we can say that it's a toolkit for applying transformations to GHC's core language programs interactively. Okay? So interactive is a key thing here. Okay? And this is a system we're developing at the University of Kansas, Lawrence. Now, unfortunately, you've got to be careful not to get us confused with something else with a very similar name, which is this guy here, the Kansas Hermit. So if you Google for us, you might get him by accident. Unfortunately, he beats us at the moment. But to the best of my knowledge, he's not a functional programmer. He might look like one, but he's not. He's certainly never encountered Hutton's razor before. Okay, so here's our Hermit. Okay, this is a high-level overview of the project. Just to give you a flavour for what's going on. I don't want to get into the details. So here on the left-hand side of the diagram, we've got the GHC that you're familiar with. You take the Haskell module, you feed it to GHC, it compiles it and spits out a binary at the end. All well and good. Now what we're doing is we're using GHC's plugin mechanisms, plugins mechanism which is a new feature of GHC that recently came out about a year ago, which allows access to GHC midway through compilation, this arrow here. And this is the point that HERMIT gets in. So GHC pauses, and we allow you to interactively experiment with what you've got. So I'll just talk you through the main components of the HERMIT system. So at the bottom of this diagram here we have something called Cure. This is a strategic programming library we've implemented. We've put this on Package as an independent package, but it's designed with HERMIT in mind. And that provides a traversal mechanism for traversing tree structured data or directing transformations to certain points in trees. And then we've specialised Cure to the GHC core language and built a load of operators specifically for GHC core, and then we've built some rewriting primitives, just basic transformations like beta reduction, eta expansion, that just case analysis, things like that, just primitive rewrites over the GHC core language. And we reflect these as a bunch of commands available that you can then interactively apply. So you can say beta reduce this, for example. This is all part of what we call the HERMIT kernel, which is a version control system. So as you modify your program, it automatically keeps track of old versions, and you can backtrack. So you can apply various transformations. You can decide, no, that was a mistake, I'll backtrack, I'll branch off, I'll try something else. And it maintains this version control tree, so you can try out different things at once. And the idea is we have this kernel, and then onto this kernel you can plug in various applications. So we've got some applications already, and we're hoping other people will come and use our kernel as well. So I'm going to demo today the HERMIT shell. This is a command line shell, allowing you to just interactively, you type in a command, you see what transformation it applies, it prints out the tree, and then you can apply something else. And I'll demo that in a few moments. We're also building a HERMIT server with a RESTful API, so you can plug web services into it. We've got some new students who've just started. There's about 8 people working on the project at the moment. And we've got these new students who've just started and working on GUIs to interface with this, to give you a clear view of what's going on. And we've got some other components that make it all work, but I want to talk about that today. So I think the best way, well, first of all, let me say it's on Package. You can download it today and try it out, provided you've got GHC 7.4. Okay, so we use some fairly modern features. You need at least 7.4, and unfortunately we've had a few issues with GHC 7.6, which we're going to fix in a few days, but right now you need to use GHC 7.4. But provided you've got 7.4, it should be easy enough just to get it from Cabal and install it. And we provide a HERMIT command, which you just run on your top level Haskell file. And all that does is invoke GHC with various default flags that we found useful. The only one that's important is this plugin equals HERMIT here. This invokes the GHC plugins mechanism. The rest of them, not important, don't worry about them. We just found them convenient. So let me demo this. I think that's the best way to understand what's going on. So I'm going to do a very, very simple transformation. It's not that interesting, but it'll show you what's happening. So here we have the classic Fibonacci function. And I'm going to transform that by taking the recursive calls to fib and just unrolling them once, so that we get a program that looks like this. Okay? So it's not a very interesting transformation. It is a very slight optimization. It speeds up fib by about 20% because there's less function calls being made. But it's not overly interesting in and of itself. So here's my Haskell source file. I want to show you this just so you can see there's nothing funny going on. Right? There's nothing funny in that source file. It's very basic. And what I'm going to do, I'll just clear this to start. I'm just going to invoke HERMIT on that file. And what this will do is it will call GHC with HERMIT plugin flag, and then it will pause GHC midway through compilation. Okay? So it started compiling, it's scanned, it's parsed, it's type checked, and now it's paused, and now we're in HERMIT, and HERMIT is displaying the contents of the module. So you can see we've got a fib function. We've also got 2 main functions. That's just a GHC thing. GHC creates an extra main function. That's nothing to do with us. That's someone who knows that, if you want to know. So I was interested in the fib function. So I'm going to tell HERMIT I want to consider the fib function. And this will just zoom me into the fit function. There we go. So what we're looking at now is GHC Core, or at least our pretty printed version of GHC Core. So some surface syntax has been compiled away, so the if then else has been replaced with a case. Infix operators are moved into prefix positions. Also in GHC Core, types get passed around explicitly as arguments, which we're currently representing as these green triangles here. So those green triangles are type arguments. If you wanted to actually see the types, which often you might want to do, you can choose to display them, and you can see that there was an int in this case. Or you could hide them. Hide. Omit, maybe? Yeah. We can omit them if you don't want to see the types at all. I'll go back to the original viewpoint. Making them abstract. So these are just different settings for the pretty printer. We're not getting rid of the types, we're just getting a different view of what's there. Okay? And the pretty printer has various settings depending on what you're interested in. Now, I said what I wanted to do is unroll the recursive calls to fib. Now, I could manually navigate my way down through the syntax tree. We have some basic navigation commands like down and up. But that's a bit tedious and we don't want to do that. So I mentioned earlier we have this strategic programming library called Cure, which is designed to help us traverse trees, and that provides various combinators that do exactly what we want here. So there's a combinator called NEBU, and NEBU is it's a tree traversal. BU stands for bottom up. Okay, so it traverses the tree in bottom up order. That is in a post order traversal, I think. So we start at the leaves and work our way up. And the NE means go everywhere all over the tree, try and do this everywhere and succeed if it succeeds anywhere. And the inline fib just says apply the inline transformation. So I do that. There we go. So the recursive calls to fib have now been inline, so there's quite a lot of code there, so you don't need to read it all, but you can see that we've got one recursive call to fib here and one here. Okay. So that's all I wanted to do. So now I can just issue the command resume, which says give this code back to GHC and let GHC continue compiling. Okay, and it does so. So now we've compiled a slightly different version of fib. I won't actually run it right now. I've got a more interesting example to run later. First of all, let me show you here's some examples of some HERMIT commands we have. So we have about 100 different HERMIT commands available at the moment, and we're adding more every day, but just to give you a flavour, we have rewrites specific to the GHC core language, such as inline and case splitting. We have these strategic traversals, so you can traverse anywhere over the tree, you can repeat a rewrite multiple times and keep repeating until it can't change anything anymore. We have these navigation commands for wandering around the tree. We have a whole version control system, so you can keep track of what transformations you've done, backtrack, you can save what you've done as a script, and you can load scripts and run them, things like that. Okay. I'll take a little diversion now. I want to talk about GHC rules. So this is a GHC language feature. I guess many of you are familiar with GHC rules already, but for those who aren't, here's a sort of lightning overview. Okay, so this is a feature provided by GHC that lets you encode custom rewrites in your Haskell source files with these fragments. And what this says is replace the thing on the left-hand side with the thing on the right-hand side if GHC encounters it anywhere in your code when it's optimizing. So what HERMIT does is it makes these rules available inside the HERMIT system as commands. So anything you write as a rewrite rule in your source file, it's available in HERMIT. And we claim, though we don't have a lot of evidence to back this up yet, I admit, that HERMIT could be a useful tool for testing and debugging rules. If you're a Haskell library writer and you use rules a lot, and sometimes they're not firing when you think they should fire, or they're not doing exactly what you expect, you could load them up in the HERMIT system and navigate and exactly try them out where you want and see what's going on. And we've certainly found this useful when we had rules that weren't firing, but we expected to fire due to technicalities of the GHC core language. Okay. But the main purpose of this is to be an easy way for users to write their own HERMIT commands, essentially. Okay, so I'm going to give another demo now, something a little more interesting. So this is the reverse function, and this is, at the top we have the classic inefficient reverse function. and down below we have the more efficient reverse function that uses an accumulator. So the top one is quadratic time, bottom one is linear time. Okay, so this, I'm going to guess this is a transformation you're pretty familiar with. So I'm going to use a technique called the worker-mapper transformation to encode the transformation steps from the first one to the last one. If you don't know what that transformation is, it doesn't matter. It's just a formal reasoning technique that you can use to transform programs. So let me open that up. I already opened it already. Reverse. So here's my Haskell source file. So we've got the reverse function at the top. I've written in these additional functions wrap and unwrap. They're to do with the worker-mapper transformation. Don't worry about them if you're not familiar with it already. You can see I've encoded something as a GHC rule because I want to be able to do that within the HERMIT system. So the validity of that rule, it comes from the worker-mapper transformation. It's not something that we check or the GHC checks. So, in fact, let me first of all show you running the reverse function. So, without any actual transformations to that reverse function, it takes about 6 seconds to reverse that list because it's quadratic time. So, hopefully, by the time I've transformed it, that will improve. So, let's go reverse. Okay, so there we have the reverse function inside HERMIT and the other wrap and unwrap. So let's look at rev. There it is. So you can see that matches up to the rev in the code, more or less. Slight differences again due to the way GHC core is constructed. Okay. Now, I've built a script to perform this transformation. Here's what it looks like. These are all just HERMIT commands that you can just type into the command line, just collected in script for convenience. And I don't have time to go through all of this, so I'm just going to load it up and run it. So let me backtrack to the beginning and just load up that script. Okay, so HERMIT says it's loaded all those 33 commands and applied them, and now it's showing the final result. Okay? And this is the efficient version of reverse with the accumulator. You can see that we now take the accumulator, and when we get the empty list, we return the accumulator, otherwise we just add the argument into the accumulator, which is what we want. Okay, so that's the efficient version of reverse. If you want to see what we've done, I can call up a log which shows you all the commands we've applied, and you can backtrack to any point along there, to any previous stage if you so want. But I'm happy now, so I'm just going to pass this to GHC. Loads, and now, if I run that, it should now run in linear time rather than quadratic time. So before it was 6 seconds, and now it's instantaneous. Okay? So you can see that's the actual transform code that's been compiled. Right. So really, that's all I want to say today. I just wanted to give you a flavour for HERMIT, what's going on and what we're developing. It's still very much in the early phase of development. We're very much in the process of adding new features. I mentioned earlier we want to plug in lots of applications on top of our kernel. This command line is just one such application. We're particularly interested in building an equational reasoning framework, so you can actually put your equational reasoning proofs into HERMIT and demonstrate equivalence of your Haskell programs. But that would involve a much more restricted application, because at the moment we do have some transformations that don't guarantee preserving total correctness. You can introduce non-termination. We also have a paper at IFL this year, or at least a draft proceeding so far, which talks about some of our experiences of taking known transformation techniques and actually coding them inside the HERMIT system, if you want further reading. What we're particularly interested in is your feedback. We're hoping that people go away and try our system, and you particularly tell us what features you want. There's lots of directions we can take the HERMIT system in, lots of applications we could build, so we want to know what's useful for the Haskell community and what you really want to be able to do. So please get back to us and let us know. There are two other members of the team in the audience, Andy Gill and Andrew Farmer, here at the front, so talk to them or me if you have any questions. That's all, thanks.